The next topic has to do with multiplying and dividing radical expressions. We're first going to take up multiplication of radical expressions. Suppose we have the following. Suppose we have a square root of 6 minus the square root of 3. Well, this is nothing but simply working with a distributive property. We have something on the outside and the quantity on the inside. Distributing that, we're going to have square root of 6 times the square root of 18 minus the square root of 6 times the square root of 3. Nothing different than what we've had before. But now, since we're multiplying two radicals, we have a property which says that if the radicals are real numbers, we can say it's the square root of 6 times 18 minus the square root . Find these out, let's just go ahead and break them apart. 6 is the same thing as 6, and 18 is the same thing as 6 times 3. Of course, I could have broken down the 6 as a 2 times 3, and this is another 2 times 3. But if we can find numbers that are perfect squares that are a little bit bigger, then we're going to reduce our work a little bit. For the second radical, I am going to have to break that 6 down into 2 times 3. We've got a perfect square inside the radical, 6 times 6. We can remove that to the outside. It becomes 6 on the outside. 6 times the square root of 3 minus, we can remove the perfect square here to the outside. The 9 comes out as a 3 times the square root of 2. So we've got 6 square root of 3 minus 3 times the square root of 2. And that's as far as we can go. Of 3 and the square root of 2, they're not like terms, and so that's as far as we can go with that simplification. So if we multiply a monomial times a binomial, just use the distributive property and simplify the radicals. What happens if we multiply a binomial times a binomial? For example, suppose we have the square . With multiplication, notice that in the previous example, we were able to combine that product inside the radical, and only because both of these radicals were to the same order. And that's important, that both the root and the other one had been a cubic root. So that's one thing to watch with these problems. All right, going back to binomial times a binomial, however you've learned to do the problem of a binomial times a binomial works here also. Whether you use FOIL or whether you simply remember to multiply each term by every other term, it doesn't make any difference. As so before, we can combine that product inside the radical. Now let's multiply the square root of 3 times the negative 5. That will give us minus 5 times the square root of 3. 2 times the square root of 6 is going to be plus 2 times the square root of 6. And finally, the plus 2 times the minus. If you're comfortable using FOIL, be sure and do that. Whatever you're comfortable with, as long as you remember to multiply every term by every other term. All right, this first radical has factors. What we know that we can change 6 to 3 times 2, and so we do have a inside, we're left with the square root of 2. For the next one, we're going to leave that as it is. There's nothing else we can do with that. The same thing for the third term. We have this term without the radical. So now that we've multiplied everything, let's see if we can combine any of the terms, but none of them are like terms because this is a square root of 2 term, square root of 3 term, square root of 6 term, and this has no radicals at all. So that's as far as we can go with that problem in multiplying it out and trying to simplify it. An example where we have some roots of a higher order. For example, what about 7 plus the cubic root of 6? And suppose we multiply that by different than before. We've got a binomial times a binomial. As long as we know that we have to multiply every term by every other term, we'll be fine. Let's start with 7. Let's multiply 7 times 5. That gives us a 35. Let's continue. 7 times the cubic root of 6. That's plus 7 times the cubic root of 6. Now we'll take the cubic root of 6 in the first factor and multiply times 5. That will give us 5 times the cubic root of 6. And finally, we'll take the cubic root of 6 times the cubic root of 6. Be careful with that term. So we have a 35 plus 7 times the cubic root of 6 plus 5 times the cubic root of 6. And there we've got two like radicals we'll be able to combine. And then finally over here, we've got the cubic root of a certain number, 6 times 6. But we know that 6 is the same thing as 2 times 3, and the other 6 is the same thing as 2 times 3. And you notice we've side. However, we can combine these middle terms here. We've got 7 of these radicals and 5 of these radicals. They are like radicals, so we have a total of 12 of these radicals, plus the cubic root of 36, and there's nothing we can do with that. No other terms can be combined, and that's as far as we can go with that problem. All right, now, one of the important things in multiplying these binomials is the square root of 3y, and suppose we're multiplying that by the square root of 3y plus the square root of x. When you look at this problem, you might notice already that every your minds that is these are the factors of the difference of two squares. So just to remind you of that multiplication, if we have a plus b times a minus b, when you multiply this out, however, with two squares, a squared minus b squared, and that's called the difference of two squares. Because notice over here we're going to have a plus ba term, and over here we're going to have a minus ba term. Those middle terms disappear, and we end up with the square of the first number minus the square of the second number. Well, that's exactly what we have right here. We have a first number minus the second number, and a first number plus the second number. Simply say that those radicals, the product of those radicals is going to be the first number squared, just like we have the a squared right here, minus the second number squared. And our second number in this case is the square root of x squared. But notice what happens up with simply the quantity on the inside, because we're assuming all the variables are positive numbers. And the same thing for this one. If we square the square root of x, we end up simply with an x. Notice what's happened. We started out with this problem right here that had several radicals. But we were able to multiply these out and eliminate the radicals. And that happens whenever we've got the factors of the difference of two squares. Because when you multiply those out, it's the square of the first. That we're going to be using later when we divide numbers with radicals in the denominator, and we have binomials in the denominator. So it's something to remember for later use.